On the morning of the 14th of June 1940, several German tank divisions rumbled through the streets of Paris. The impossible had happened. Germany had invaded, and France had fallen. But there was one building on the outskirts of Paris that the Nazis never occupied. This chateau has the same status as an independent territory. Its contents are so closely guarded, I have to hand over my passport to gain access. Today, an eminent group of scientists have gathered from all over the world to witness a very special event. Security is tight, with key holders arriving from 3 different countries. The vault holds one of the most important artifacts in our world.
This is a real piece of measurement history. Well, I suppose not really history at all, because this is the kilo.
Under 3 layers of protective glass is the kilogram master, known as Le Grand K. It's the weight on which all weights have been based since 1889. Its importance is so great that neither the Nazis nor the liberating American forces dared set foot inside here. And the reason we're here today? Well, just to check it's still here. But there's a problem. Tests have revealed that Le Grand K, this scientific celebrity, is losing weight, creating a crisis in the scientific world. It's losing approximately 20 billionths of a gram every year. But why on earth should such a tiny change matter so much?
I'm on a journey to investigate the world of measurement and to see how our drive for precision has really changed the course of history.
Today, we can describe the chaos and complexity of the universe with just 7 fundamental units, the building blocks of modern science. And science is obsessed with defining these units with ever greater precision. In this series, I want to understand why such extreme levels of precision are so important, how we define these units, and how, through history, each step forward has unleashed a technological revolution. In this program, we'll explore why being able to measure weight is so important, and how the race to replace the aging Grand K might hold the key to a new way of understanding our world.
This is the story of how we mastered weight.
How much do I have is a question that has driven trade and commerce since the dawn of civilization. And today, weights are still central to all our lives. The reason we're so reliant on weights and scales is in part down to our own inability to accurately gauge weight. We tend to believe our eyes rather than trusting the weight in our hands. And I've come to London's Borough Market to prove the point.
Excuse me? Wonder whether I could get you to take part in a little experiment.
Yes.
Yeah. So I've got a series of weights here which I've just put in order of height. What I'd like you to do is to place the heaviest weight here and the lightest one at your end. Have a go. See which one you think is the heaviest.
That's
This,
Definitely,
the
yes.
little guy
The heavy-
here, okay,
yeah,
that's the
yeah.
heaviest. Okay, what about the next heaviest?
I think this one, yeah. It's the lightest.
The lightest of all?
I think.
Okay.
Yeah.
Now, the really surprising thing is that the one that you've put at this end, which you think is the lightest, is in fact the heaviest. And this one here, so you thought this was the heaviest. Okay, I'm going to
Yes.
give you both of these in your hand. This one is actually heavier than that one. Do you believe me?
Well, it doesn't feel like that.
No, it doesn't. Now, let's use the scales. So I'm going to weigh the one that you thought was the lightest. So that comes out about 424 grams. Okay, let's put your one on. You think this one's heavier? It's only 345 grams. Isn't that extraordinary? Because even with that knowledge, now try and weigh them again. Would you say which one's heavier? I know, absolutely true. And that's why we need a set of weights, because we're so bad at the perception.
Like any good scientist, I carried on with the testing.
How is that possible?
And my random shoppers, to a man and a woman, all chose the same 2 weights. And they all chose wrong.
Okay, well,
Seeing if something is big or small massively skews our perception of how heavy it is. It is a problem our ancestors first started grappling with more than 5,000 years ago. Our earliest evidence comes from the Middle East and was driven by the emergence of the first cities in Mesopotamia around 3000 BC. As populations grew, a way of fairly trading goods was urgently needed. People demanded a system of weight that everyone could trust. Taking their inspiration from nature, they used grain. Uniform in size and shape, grain was available to all. The world had its first weights. Using simple beam balances, which we continue to use today, we started to trade goods based on their weight in grains. It wasn't perfect, but with grains varying so little in weight, the system worked. It made the movement and sale of goods possible, enabling humans to live together in bigger cities and allowing the first economies to grow. Empires were no longer being built solely by armies. They were being built by trade.
As commerce developed across the ancient world, a faster means of weighing produce was needed. After all, if I wanted to buy something that weighed 700 grains of barley, I don't want to have to count out 700 grains each time. So gradually, a standardized system of weights began to emerge. First, the Mesopotamians, then the ancient Egyptians developed stones and things made out of metals and brass in order to represent different weights of grain. It was such an efficient system that it began to be copied across the civilized world. So here we have standard weights from China. These hexagons are standard weights used in Sudan. And the amazing thing is that despite all of these different weights and measures, they were all related back to the weight of a grain, because everyone trusted how much a grain would weigh.
By Roman times, millions of tons of produce were being traded around the world every day.
The ability to compare the weights or masses of 2 different kinds of goods so that you can work out how to exchange between them, that's the key to economic success. And so it's the demand for economic comparison that drives weight standardization throughout history.
By the end of the 13th century, the world had hundreds of different weights, and nearly all were based on a fixed number of grains. In England, we'd inherited the pound from the Roman Empire. It was initially made up of 12 ounces, which were equivalent to 437 grains of barley. But the problem all rulers faced was how to keep weight standardised across a nation. It was considered such a big issue that even the Magna Carta, the most celebrated legal document in English history, tried to deal with it. Let there be one measure of wine throughout our whole realm, and one measure of ale, and one measure of corn. It all sounded great in theory, but in practice, it was virtually impossible to enforce. Cheating was such a big problem. Regular trials were held to check merchants' weights and measures. Any found to be wrong were immediately destroyed. Accurate scales were the only way cheats could be exposed. Accuracy was power.
Scales were not only a great measuring device, they also came to symbolise fairness, power, and the very legal system itself.
From ancient Egypt's feather of truth to the paintings of the great Dutch masters, scales have featured throughout history.
As it was written in the Bible, by weight, measure and number, God made all things.
Measurement has always been associated in culture with justice and law and crime, because what it does is to establish the equivalence between two things that you otherwise could not compare. That's what justice means. So it's no coincidence that the figure of justice is shown carrying scales, carrying balance pan. And for centuries, when you made a weight measurement, you had to show your customers what you were doing, partly to avoid the possibility of deceit, but also to show how just you were. To be just was precisely to use balance.
So with all this moral weightiness flying around, the punishment for using false measures could be severe. In 1772 BC, the Code of Hammurabi was introduced into Babylonian law, which said that any taverner using false weights could be served up with a death penalty. And in the 18th century, bankers caught cheating would have to stand in pillory, and brewers in the dung cart.
But despite the importance we placed on weight and getting it right, it took one remarkable Englishman to realise the measurement of weight has a fundamental problem. It was the great Sir Isaac Newton who first realised that weight changes depending on where and when you are measuring it.
It was 1665 and Britain was gripped by the plague. So Newton decided to flee his college in Cambridge and he came to the safety of his country retreat here at Woolsthorpe Manor. And here is the famous apple tree that inspired his observations. So much has been written about this apple tree. It really has become a symbol for the turning point in our understanding of the universe.
Newton's eureka moment was witnessed by a friend. After dinner, the weather being warm, we went into the garden and drank tea, under the shade of some apple trees. The notion of gravitation came into his mind. why should that apple always descend perpendicularly to the ground?
Newton realised that there must be a force acting on that apple, pulling it to the ground. Otherwise, why wouldn't it just float in the air or move sideways or go upwards? He named that force gravity, after the Latin word gravitas for heaviness.
Newton's law of gravity was to completely change the way we think about weight. We finally understood the subtle but vital difference between weight and mass. And it paved the way for modern measurement.
Now, to show how important Newton's discovery was, I've got a piece of metal here, an incredibly sensitive set of scales. Now, the scales say that this piece of metal weighs 368.70254. It's kind of flickering between the two, it's so sensitive. Now, let's take this piece of metal to the top of this block of flats and see how much it weighs up there. Now up here, the metal weighs 368.69 grams. So I seem to have lost 10 milligrams. But of course, the mass hasn't changed. What's changed is the gravity. I've got less gravity up here than I have got down at the bottom of the block of flats. And if I took this piece of metal another 100,000 meters up into space, then it would weigh hardly anything at all. Simply put, mass is measuring the amount of stuff there is inside here. And that doesn't change whether I'm at sea level or out in space, but the weight does.
In one simple equation, Newton's genius revolutionised how we thought about weight and mass. But it would take a real revolution in France to finally create the measure of mass that we all use today, the kilogram.
By the middle of the 18th century, weight measurement, like length, was in a total mess. Nobody had it worse than the French. People were supposed to use the king's measures for pounds and ounces. But in reality, every village and town had their own system, all slightly different. Disputes and arguments were so commonplace that the village took to chaining the weights and measures to the wall of the local church.
Trade was painfully slow and open to corruption. And no one could agree on whose weight was right. A new international system of measurement was urgently needed. Letters flew between the powers of Europe. Too long have Great Britain and France been at variance with each other for empty honour or guilty interests. It is time that the two free nations should unite their exertions for the promotion of a discovery that must be useful to mankind. On the eve of the French Revolution, the great and good of the French scientific community approached the doomed Louis XVI for permission to create a new system of length, mass and volume measurement. The greatest minds of the day gathered here at the prestigious Academy of Sciences in Paris to brainstorm a solution. They decided to base their new system on something universal and unchanging: the Earth. It was the birth of metrication. The first unit they fixed was the metre, basing it on 1/10,000,000th of the distance between the North Pole and the equator. The next was the kilogram, and the task was given to the father of modern chemistry, Antoine Laurent Lavoisier. By day, he was a wealthy tax collector. By night, he was the greatest chemist in the land. The French visionaries behind the metric system wanted all the new measurements to be linked, so they came up with an elegant solution. The new kilogram was to be equal to the weight of 1 perfect cubic decimetre of water, a litre.
The idea was very simple. Anybody with a meter ruler and some water could create their own kilo. But making a kilo based on the weight of a cubic decimeter of water turned out to be much more difficult than they thought. Now, I've got 2 perfect decimeters of water here. The trouble is that these don't weigh the same amount. The colder water weighs 998 grams, whilst the hotter water, 957 grams.
Because the hotter water is, the less dense it is.
And that's the trouble, the weight depends on the temperature. Not only that, it'll depend on what impurities are inside the water, what the atmospheric pressure is, how far I am above sea level. There's a real problem with trying to define the kilo based on the weight of water.
Lavoisier came close to solving the problem of how to accurately weigh water. But his brilliant career met an abrupt end at the hands of the guillotine on the 8th of May, 1794. His tax-collecting day job was his downfall. Next to take up the kilo challenge were scientists Louis Lefebvre-Junot and Giovanni Frabroni. 4 years later, they finally perfected how to measure a cubic decimeter of distilled water. A master metal kilogram could finally be cast.
And on the 22nd of June 1799, they presented their prototype kilogram to the nation. Called the Kilogramme des Archives, it was made out of the new wonder metal platinum. Soon, kilogram clones, as well as copies of the meter bar, were being sent to villages and towns across the nation to bring uniformity to the French Empire.
Their vision was brilliant. But there was a flaw.
The trouble was that pure platinum, although resistant to air and water, is actually rather soft and prone to damage.
And that meant bits were easily knocked off, gradually rendering the hundreds of cloned kilos inaccurate. The Academy's grand idea was slowly being eroded. It would take nearly 70 years to realise a new, more stable master kilo, and then a set of clones would be needed. London metallurgists Johnson Matthey were given the order to produce 250 kilograms of platinum mixed with strength-giving iridium. It was a big order, worth £2.2 million at today's prices. The man in charge of production, George Matthey, the world's leading expert in casting platinum, offered to make the kilos at his state-of-the-art furnaces at Hatton Garden. But French pride intervened, insisting it happened here at the Conservatoire in Paris.
It was a disaster. The platinum got contaminated by iron, rendering the whole consignment useless. It was a huge embarrassment, both for French pride and their pockets.
But it wasn't the death of the kilo or the metric system. With international trade booming, the benefits of having one common measurement system were clear for all to see. And in 1875, diplomats from 17 countries met here in Paris and agreed to formally adopt the metric system. With great zeal, a new kilogram master was commissioned. The order once again went to Johnson Matthey, and this time George Matthey was finally allowed to cast the most accurate platinum and iridium kilo ever made. Christened Le Grand Quai, it was consigned to a specially made vault at a newly established international centre of measurement outside Paris.
And here it is,
the Bureau International des Poids et Mesures, the BIPM, or in English, the International Bureau of Weights and Measures. And this is really international territory. It's kind of a mark of how important measurement is to the world, that we've created a UN of measurement.
From the beginning, the BIPM's mission was to make sure measurements were consistent throughout the world. This is the building that was once home to all the world's master measurements. Today, most have been retired, replaced by new definitions based on the universal and unchanging laws of nature, like the speed of light and the movement of atoms. Le Grand Quai is in fact the only artifact that is still in use, a measurement dinosaur.
Today, here at the BIPM, they're still making clones of that Grand Quai. Fabrice here is polishing this until it exactly matches the mass of Le Grand Quai sitting in the vault downstairs.
Over half the countries in the world have one of these clones.
The next one he's working on is clone number 103 that's going to go to, well, we're actually not allowed to know where it's going to go.
Without Le Grand Quai, our entire global system of mass and weight measurement would crumble.
Unfortunately, crumble is a little bit of a touchy word inside this building, because that's what's happening to Le Grand Quai. I mean, it's not literally crumbling, but despite the kid-glove treatment it's received over the last 150 years, it's believed that it's changed by the equivalent of 1 grain of sand during its lifetime.
And that's bad news, because it no longer matches the weight of the world's clones. A new way to define mass is urgently needed.
Now the race is on to replace the definition of the kilo with something more fitting for the 21st century, something based on a universal constant that can be measured wherever you are in the universe. We've done it for length, that's now tied to the speed of light. For time, that's related to the movement of electrons in the atom. Now we want to do it for the kilo.
It's a head-to-head race between 2 international teams, each one taking a radically different approach to solving the kilo crisis. In America, Team Watt Balance are combining the power of electricity with scales whose principles date back 5,000 years. Their dream? To redefine the kilo based on energy. 6,000 kilometers away in Germany, Team Silicon Sphere are trying to count every single atom in a perfect ball of silicon. It's an immense task, like covering the Earth in sand and trying to count every single granule. As the best minds in measurement science fight it out, Le Grand Quai's long and illustrious career could soon be over. But its legacy has been staggering. From the moment it was adopted, the movement and sale of goods became much easier and more efficient. The scientific community jumped on the new metric system, loving its simplicity and the ease they could split or multiply the metre and the kilogram by 10. But from the very beginning of its life in the 18th century, the public remained less convinced.
People were just not interested in revolutionizing their everyday life, what they did when they went shopping, how they exchanged and bought in the name of revolutionary purity.
The kilo continues to divide opinion. In the UK, it was only adopted in the 1960s. And its arrival was met with outright hostility.
All we ask is the freedom of choice to record in the native and still legal measures of this country instead of these cockeyed kilograms which make no sense at all.
But despite the opposition, today all but 3 nations, the United States, Liberia and Myanmar, have embraced the kilo and the metric system. While the world was moving towards a unified weight measurement system, the actual technology of weighing was now lagging behind. Variations on ancient Mesopotamian and Egyptian beam balances remained our scales of choice right up to the 19th century. The problem was, they took so long to use. In the UK, weighing was made much worse by the Turnpike Act of 1752. Eager to tax the movement of goods, the government ordered all towns to erect a crane machine or engine for the weighing carts and wagons. At each location, carts had to be unloaded, weighed, reloaded and weighed once again. And to add to the daily misery, every key road demanded tolls too, all payable on the weight you were carrying. With the birth of the Industrial Revolution, things had to change. Factories to forges now needed raw materials in unprecedented quantities, and they had to be weighed, bought and transported with ever-increasing speed and precision. A faster, more efficient means of weighing was desperately needed. The solution was the weighbridge. A technological triumph, the weighbridge, with its balance scale hidden beneath the floor, would play a key role in driving our industrial revolution onwards. Now, loads could be weighed in seconds as they rolled on and off the bridge. But it would take electricity to drive the next big breakthrough in weighing. Inventor Charles Wheatstone championed the use of electricity in the 1840s. Experimenting with simple electrical circuits, he devised a way of measuring electrical resistance. But it wasn't until a century later that people realised this very same technology could be used to measure weight. Today, the need for speedy mass measurement drives our world.
This train is delivering coal to Rugeley Power Station, and as it runs over the track, it's being weighed by load cells which are underneath the track. If we come in here, you can see how much we've weighed so far. So hi Andy.
Hi.
So this is the first carriage that's gone over, so we've got 100 tonnes.
Yeah.
They're much more efficient than sort of weighing it all by hand.
Oh yeah, very much so, yeah. And we can measure at 70 kilometres an hour, so you're talking less than a second per wagon probably.
Wow, that's extraordinary.
Yeah.
So how's this piece of track actually weighing the train? Well, underneath the track are several of these. They're called load cells. And actually, it's this little system of wires on the rod which is doing the weighing. But as soon as something runs over the track, it compresses the rod and the wires get shorter and fatter. The resistance goes down and I get more electrical current running through it. And suddenly I'm getting a reading. What's amazing is that there's a direct mathematical relationship between the increase in electrical current and the weight going over the wires. So we're using the electricity to weigh the train. In fact, this thing is so sensitive that even if I step on it, I actually can get how much I weigh. So let's see. So how much do I weigh, Andy?
84.
84 kilos?
Yeah.
Don't weigh 84 kilos. Must be the weight of this.
Today, load cells are used the world over. We've come a long way since the days of the beam balance. Now everywhere, from roadside weigh stations to supermarket checkouts, use them. Measuring mass with electricity has changed our world. We can now weigh, transport and deliver billions of tons worth of produce with a speed and accuracy our Victorian forefathers would never have dreamt possible. Precision mass measurement is key to world commerce. Now, it's the turn of the very small to push the limits of mass measurement. Here in America, I've come to meet a team who've come up with a unique approach to measuring some of the smallest living things on Earth. Cells. Project leader Scott Manalis is using mass to monitor the growth of cells. His work could one day revolutionize our fight against cancer. In his lab, he has built the world's smallest weighing station. Here, inside a microchip just millimeters in size, cells are captured and passed over a sensor. The long, thin section, highlighted here, acts a bit like a diving board. When a cell passes over it, it vibrates, just like a diving board moves after a diver jumps off it. The speed of the vibration is directly linked to the weight of the cell. So using simple maths, Scott can measure the cell with incredible accuracy.
This cell is equivalent to like a white blood cell in terms of its size.
Okay.
And it weighs 100 picograms. So
Picograms, so that's
10 to the minus 12.
Oh, right, okay, so 0.
Lot of zeros.
Lot of zeros.
Lot of zeros
So this is
to
an
go.
incredibly small thing.
So the
you're
cell
measuring.
doesn't weigh very much.
Yeah.
And the precision at which we can weigh it with is 4 orders of magnitude below that.
Wow, that's incredible.
So that's 10
precise.
femtograms. So femto now takes us from
So
minus
part
12
in
to
1,000
to 15.
Right.
1 part in 10,000.
10,000.
0.01%.
Exactly. Yeah.
We care a lot about these things.
Yeah, no.
We're soon in the domain of extreme numbers. But what's amazing is Scott's measuring the weight of a single cell to within 1,000 trillionth of a gram. His work is revolutionizing our understanding of how cells grow. And by measuring how cells respond to a drug, it could lead to personalized and far more effective cancer treatment. It's absolutely amazing the limits we are now pushing mass measurement. But scientists are frustrated. And it's because we're still trying to tie mass back to that aging lump of metal in Paris, Le Grand K. And with Le Grand K's weight unstable, there's a real urgency to find a new, even more accurate way to define mass. Now, a race is being fought across 2 continents to retire Le Grand K. "20 miles north of Washington is one of the world's most accurate set of scales.
This whole area is a car-free zone, and that's because the scales that are being used here are so sensitive that even the magnetic field caused by the metal inside the cars can affect the measurements. Welcome to Team Watt Balance.
Most things in this strange-looking building are made of wood and clad in vinyl to minimize the effects of magnetism. Everything from the power lines to the plumbing pipes are encased in shielded plastic ducts. And every single bit of metal that enters the lab, down to this tiny spare part, has to be checked for its levels of magnetism.
point out to you this building. This is all a wooden structure. And there's no...
Stefan Schlamminger's project is one of the longest-running metrology experiments in the world. Its founders have long since retired, but now the team here are close to fulfilling their dream. And this is their brainchild, the Watt Balance. Inside this cage of pure copper is a weighing scale whose principles go back to the very first balances 5,000 years ago. And it's so sensitive, it can measure the kilo to 8 decimal places.
So here's our watt balance.
It is a thing of beauty. Wow.
It really is. And you see up here, this wheel is like the beam in an old-fashioned beam balance.
But that's quite ancient technology, isn't it?
Yeah, it's 1,000-year-old technology up on top, but down here you will see the coil that's connected to 3 rods, and this will provide the counter force to the gravitational force that this mass is providing.
On one side of the scales, deep inside the mechanism, sits a clone of the Legrand K. What's so extraordinary about this device is that on the other side, instead of a weight, the team are using electrical force to counterbalance it.
The watt balance defines the kilogram by linking mechanical power to electrical power. That's why it's called the watt balance.
Right.
Their goal is to measure the amount of electricity needed to perfectly counterbalance the kilo clone and redefine the kilogram based on electrical power. It sounds straightforward, but when you are working with one of the most sensitive scales in the world, everything from car engines to the movement of the local deer population outside can affect its readings. Even tiny shifts in gravity, like the phase of the moon and the level of groundwater, need to be measured and taken into account when this experiment is running.
It seems you're having to keep track of so many different things in order to pin down that kilo.
That is the art.
That's the art, the art and the science of this. Oh, that's amazing.
So we try to measure this kilo to about 4 parts per 100 million. And in order to do so, we need to measure all these auxiliary quantities like voltage, resistance, gravity, meter, second, to much better than 4 parts per 100 million.
Now, after more than 30 years of perfecting the scale's accuracy, Team Watt Balance are very close to achieving their holy grail, a new electronic kilogram. I left the Watt Balance team realising I was witnessing a potentially historic moment in the life of the kilogram.
The days of the American kilo making its transatlantic journey to Paris to be compared against Legrand K are probably numbered. But the Watt Balance team have got a rival. In Germany, Team Silicon Sphere have got a completely different approach to redefining the kilo. And it involves counting the number of atoms in a kilogram of silicon crystal. People often talk about counting the number of grains of sand on a beach, but what Team Silicon Sphere are proposing to do is in a completely different league. It's like trying to cover the whole globe in sand and counting every grain.
But what are these atoms they're trying to count? It was the ancient Greeks who first came up with the word atom to define the smallest indivisible particle of matter. But it took Englishman John Dalton in the 19th century to shed light on what atoms really are. At the time, we knew that all matter was made up of different elements, like carbon and oxygen. Dalton's brilliance was a radical theory that each element must consist of atoms of a single unique type and mass. Dalton would never have dreamt it possible to see or count these atoms. But now, in a remote lab in northern Germany, scientists are attempting to do just that. What Dalton didn't realise is the sheer number of atoms inside things. That there are trillion upon trillion inside a single kilo of silicon. And it's by counting these atoms that the Silicon Sphere team hope to redefine the kilo. This is a perfect kilogram sphere of pure silicon. The culmination of 30 years' work. It represents one of the most ambitious challenges ever to be undertaken in measurement history. Like the Watt balance, the Silicon Sphere project started in the 1970s.
The goal was to measure the atomic distances, also the distance between the atoms in a very perfect crystal. Silicon was at that time a material which was used for the semiconductor industry and was the first very perfect material for that use.
Silicon atoms line up in an extremely rigid and regular pattern, which in theory makes them easier to count. The idea was to create a perfect sphere of silicon, measure its dimensions with extreme precision, and then calculate the spaces between the atoms using a technique called X-ray crystallography. Then, using simple maths, they could work out the total number of atoms in the sphere. The project was supposed to take a couple of years, but they faced many challenges. The first was how to create a perfect sphere. The levels of perfection the team was seeking were beyond the capabilities of any machine. They scoured the globe and found the only way to create a sphere to the level of perfection they needed was to do it by hand. And only one man was capable of this: Australian lens maker Achim Leisner. He literally used his hands to shape the ball to such an incredible level of perfection that if you likened it to the Earth, the level of its surface would never vary more than a few meters. Using his extraordinary sense of touch, it's said Achim could feel silicon's atomic structure with his fingertips.
You need really a feeling how many atoms you have to remove on that side or on the other side of the sphere. So he had an atomic feeling in his hands.
It took months for Achim to perfect his sphere. Finally, the task of analysing the space between the silicon atoms could begin. But on the cusp of realising their dream, disaster struck. There was a flaw in the very makeup of the silicon.
In its natural state, silicon consists of 3 different forms called isotopes. Now, each different atom has a different mass. Leisner's sphere contained all 3 different types of these atoms. The team needed a pure source of silicon, or else the project was over. The solution came from an unlikely source.
A nuclear weapons facility.
The Cold War was over and a lot of centrifuge in Russia were not running for nuclear weapons. So we were lucky to rent some of this centrifuge to prepare silicon for our purpose.
A new batch of silicon was sent to Russia and spun in the same centrifuge that was formerly used to enrich uranium. This forced out the wayward extra isotopes, producing pure silicon-28. Then Leisner had to start the job of polishing all over again. Finally, after many years, the scientists once again started counting the space between the atoms. And trillions of atoms later, they've nearly completed their task.
We hope that in 2 years we will have all the information together for a new definition. That means we have a value with a very small uncertainty, let us say below 2 × 10⁻⁸.
And that's an accuracy to 8 decimal places. It's the same level of precision as Team Watt Balance in America are striving for.
At the moment, we are in the, let's say, in the pole position to win this race.
Within a few years, Le Grand K could be retired. But the work here could revolutionize another of the 7 fundamental units we use to describe our world.
Ein Kaffee mit Milch, bitte? Yeah, thank you. If the silicon team is successful, then they won't just redefine the kilo. They could end up redefining the SI unit most feared by chemistry students across the world, the mole.
It's a word which comes from Latin, meaning massive heap of material.
Now, chemists probably won't like this, but consider this cup of coffee. There's a certain ratio of milk to coffee, say 1 part milk to 9 parts coffee, which combined makes 1 part perfect milky coffee. Now, the mole does a similar thing for chemists, but replace the coffee and the milk with atoms and molecules. Yeah, perfect.
All this leads back to our friend Dalton and his work in the 19th century. When he began his investigation into atoms, he discovered that atoms from different elements weighed different amounts. At the centre of every atom is a nucleus containing protons and neutrons. Different elements have different numbers of these protons and neutrons, which is why they weigh different amounts. Throughout the 19th century, the greatest chemists of the day feverishly tried to work out the atomic weights of all the known elements. It led to one of science's greatest ever achievements, Dmitry Mendeleev's periodic table. And if you look at each element on that table, you'll see their atomic mass written just below them. It was a huge breakthrough. Chemists could finally mix and manipulate elements with newfound precision. But atoms are far too small to look at and manipulate individually. What chemists needed was a way of scaling up atomic weight into something more tangible they could weigh. And the answer was the mole.
The mole is really just a big number, a huge number in fact, which when you combine it with the atomic weight of each element, allows you to work out how many atoms there are inside something. It's the chemist's way of scaling up the microscopic world of the atom to our world of the gram. It's really the bedrock of modern chemistry, allowing us to mix things from drugs to fuel with such precision. But it leaves open one big question. Exactly how many atoms are there inside a mole?
The number of atoms that we have in a mole is what we call Avogadro's number. We can go back to Einstein, for instance, in 1905. He came up with one of the first estimates of just how big this number is, from looking down microscopes at pollen grains, and from that he was able to get one of our first estimates of the number. He got the first number right, he got the 6 right, and he got the 23 zeros right.
While Einstein's groundbreaking work got close to defining the elusive Avogadro's number, it's the silicon sphere team that could not only solve the Kilo conundrum, but also solve the centuries-old question of how many atoms there are in a mole. And once and for all, define Avogadro's number. If this happens, it will be a remarkable moment in measurement history. In one astonishing experiment, 2 golden units of measurement could be redefined.
We've come a long way since the days of using barleycorn weights. Our quest for ever greater precision has led us into the very fabric of our universe, allowing us to weigh and analyse things with incredible speed, scale and precision. In a few years' time, all going well, the BIPM will decide between atoms or electrical force to redefine the kilo. The winner is kind of irrelevant. Both Team Watt Balance and Silicon Ball have done what seemed impossible, to redefine the kilo based on the unchanging laws of the universe.
In the pursuit of ever greater accuracy, these remarkable projects have brought together thousands of years of scientific endeavour. But our quest for ever greater precision doesn't stop here. The last great measurement frontier will be to journey inside atoms themselves, to discover what mass really is. "100 metres under the Swiss-French border, at CERN's particle accelerator, scientists think that they've discovered a particle that gives things mass, the Higgs boson. And one day, our human desire for ever greater precision may even see mass redefined once more, and tied to Higgs itself.
If it happens, who knows what the technological impacts will be? And that's the beauty of measurement. Every leap in precision leads to new scientific and technological advances. Measurement has shaped our history and will continue to change our world.
Next, we explore the world of energy and how the measurement of light, heat and electricity have transformed our lives. As I continue my journey into measurement.
We've a passion for porcelain here on BBC4 tomorrow night as our Beautiful Things season kicks off at 9. There's a little taster of that coming up in just a moment. Next tonight, though, brand new Storyville from Israel with the law in these parts. Stay with us.